different occasions using YouTube tutorials featuring Matlab. Today we're looking at Lucas-Kanade tutorial, and just to say that this is not my work, I took it from Matlab Central File Exchange, and 48745 is the code there. So, and just to give this chap here, Jiwan, the full credit. Okay, so we're looking at optical flow, and Jiwan has two. There's example 2. Just go down a little bit here, just to show you what we're talking about. There's the corners detected, and then as we go on, we're able to get the optical flow. He also has another example up here, and this we have that sort of cube at an angle, and he's found the optical flow because you've just taken the picture from two different angles and you're able to measure the optical flow from the two different camera angles. So I'm going to shut those two down. Next thing, if you want to know some idea how Lucas-Kanade works, this is as good as any, embedded vision, Lucas-Kanade feature tracking. There's Wikipedia. I'm going to leave that up because I'm going to refer to that when we're looking at Jiwan's code. And then if you want to look in detail, there's Robert Collins from Penn State, and he gives a very detailed step-by-step breakdown of Lucas-Kanade. So I'm not going through it step by step. Okay, and we use convolution, so let's just look at the code here. So there's our web browser. I won't go through it line by line. We tidy up, we load in frame 1 there, and we load in frame 2. We convert them to doubles, because remember when you read in an image it's U/8, and because we're doing optical flow, we're going to end up with 1.6, 1.7, whatever it is, so we need to convert them to doubles. There's the image, there's the two images. Now, slight bit of, well, I was going to use a strong word, but let's say the optimal 2 frames are taken. Because why? Because there's clear separation between the cars. There's no overlap, and there's people walking here. So why it's idealized, we won't have one car being confused with the other, and we're assuming it's over a very short frame time or time slice, whatever way you want to look at it. So there's our 2. We very briefly resize downwards, because remember you could have very big frames, so this is kind of like pyramids that you make in image and video compression or something like that. So we resize there, we detect the corners, and then in this nested for next loop here, we dump the corners that are near the edge, because they could go off the edge of the frame and it would look silly. We plot the corners on the image. There. When it says corner there, we use Harris corner edge detection, so we have nice sharp corners, and there may be a possible overlap between that white car and that silver minivan. I want a bit of a word, but there's nice clear separation between the objects. Now we do a bit of convolution into 2D, and we're getting the partial derivatives of the image with respect to position x, y, and time t. So if I can just go back to here. So Wikipedia does there, we want to get the least squares solution of these lads here, of ix, iy, and it, and we get the partial derivatives. So just how do we get the partial derivatives in the code? There, those guys, just say we're getting the partial derivatives in the x, partial derivatives in the y, and then we convolve with the time as well. We do our least squares solution, just go up a tiny fraction. We do our least squares solution in here using the pseudo inverse here, and we get u and v, and u and v are the motion vectors in the x and motion vectors in the y direction. And then we plot the motion vectors between the first and the second frame. Hope that helps a little, and thanks very much for listening.